The University of KwaZulu-Natal's College of Agriculture, Engineering and Science committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally Center and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture engineering. The college comprises 5 schools: agricultural, earth and environment, engineering, chemistry and physics, life sciences and mathematics, statistics and computer science. Engineering is offered on the Howard College campus, agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westville campuses. Exceptions are agricultural engineering, which is offered in Pietermaritzburg, and geology, which is offered at Westville only. To compete with the best and to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. The only university in South Africa to offer accredited agricultural engineering degree, and one of only 2 universities in the country is in the world, and we have the emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers specializations. There are also degrees in land surveying or geomatics and project development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general degrees with a lot of flexibility. In this case, students have the BSc M stream. The other option is a BSc LES stream with a focus on the life and environmental sciences with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm near the Peterborough campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Okulinga, Green Valley Nature Reserve, diversity of plant and as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCOM-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understands engineering and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. College has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating. It offers food training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice, and hydrological engineering, or CRESH. It deals with the interaction between engineering and the natural environment. photography. But as for you, read.
Okay, good afternoon or good evening, I suppose, everyone. Can I just get a thumbs up, please, if you can hear me? Or can somebody indicate in the chat that? Okay, thank you, Monica. Okay, welcome to this evening session. Hopefully the connection stays with us throughout. My name is Dr. Dlamini, and I'm going to be taking you through electrostatics today, or a start on electrostatics. Helping me out in the chat, I've got Apila. So Apila is one of our PhD students at UKZN. So at any point, please feel free to either pop a question in the chat, should you have a question, or because there's a fairly low number of us in the session today, at any point, if you want to ask a question or you want me to repeat something, please don't be shy, just unmute yourself and you can stop me at any time. Also, if you feel that I'm going too slowly or too fast, please indicate that to me. Okay, so I'm going to stop with my video now and I'm going to start sharing and we are going to get to work. Okay. Okay, can I just have thumbs up, please, from somebody if you can see the screen share, if it's up for you. Okay, perfect. I got a few thumbs up. So I assume everyone can see the screen. Okay, so as I said, we're going to be doing electrostatics. So I picked some questions, not extensive questions. If you're interested in finding these questions, where I've taken them from is the 2020 paper. So they're from the 2020, what was it? It was Physical Sciences paper 1. Okay, I'll try write neatly. I don't have the neatest handwriting in the world, but we will make do. And again, if at any point my handwriting is a little bit too untidy, just again, please just let me know. So electrostatics, as the name suggests, deals with charges at rest or near rest. And so question 1 tells us that the diagram alongside shows two small identical metal spheres, R and S, each placed on a wooden stand. We're told that sphere R and S carry charges of +8 microcoulombs and -4 microcoulombs respectively, and we are asked to ignore the effects of air. Okay, so that's the setup, and question 1.1 asks us to explain why the spheres were placed on wooden stands. Okay, so the reason that you place the spheres on wooden stands is to make sure that the charge on the spheres is insulated. So it is to make sure that the charge on the spheres is insulated. Okay, because of course what happens is that the charge wants to go to ground, and so the wooden stand, wood is not a very good conductor, and so the charges can't flow through the wood to reach the earth, and that's why in theory I suppose you could use any other material as long as the material was an insulating material and not a conducting material. Another way you could say this, I suppose there's more than one way to say this, or you could say something like it is to make sure that the charge does not go to or does not leak to the ground. And either of those, I think, would be acceptable. So it doesn't have to be wood, remember, it can be any insulating material. Okay, question 1.2 is a little bit more interesting. And question 1.2 asks us to calculate the net charge on each of the spheres. So in order to answer this question, you need to remember a few things. You need to remember that when charged objects are brought into contact, what happens is that charge is going to move across from one to the other. And the way we will work out the final charge is that we take all the charges in the system, we add them together, and we divide them by the number of objects. Okay, so in this case, I've got two charged spheres, and when my two charged spheres are brought into contact with each other, what's going to happen is that electrons are going to flow from the sphere with more electrons to the sphere with fewer electrons. And it's also a consequence of the conservation of charge, basically. You should know what the conservation of charge is. So what that actually means in this case is that I bring my two spheres together, and then we separate them apart, and then the overall charge, or the net charge, I think that's what you guys call it, is the net charge is going to be equal to the sum of the charges. In this case, it's the charge on R plus the charge on S, and we divide it by the number of spheres, and in this case, it's two spheres, and so this is going to be plus 8 plus minus 4, and I divide it by 2. And if I've done this correctly, it's, what is this? It's 4 divided by 2 is 2. So there should be 2 microcoulombs. Okay, now, hypothetically speaking, basically, more hypothetically speaking, if I had 3 charges, right? If I had 3 charges, what I could then do is something along the lines of Q1 plus Q2 plus Q3, and we divide by 3, and so on and so forth. And that's the general rule in terms of how you work out the net charge on the spheres. Right, 1.3 asks us to draw the electric field pattern due to the two spheres R and S. Okay, so bit of a, I suppose it's a fairly simple question. So to answer this type of question, you need to remember a few things. The first of those is that electric fields are generally going to be represented by what we call field lines. And the field lines indicate the direction in which a positive test charge would move if it were placed in a point within that electric field. Right, that's the first thing. And the second thing is that the electric field is going to be a vector property. So I think there's basically 4 properties, right? So I'm just going to quickly summarize them before I get back to the question. It's the properties of electric field lines. Right, so there are 4 key ones that we need to know. The first of these is that your electric field lines will always point away from a positive charge. And they will always point towards a negative charge. Okay, now graphically, what that means is that if I've got a positive charge sitting in space, again, Right, so I've got my positive charge sitting in space. My field lines will always radiate outwards. So when you draw the field lines for this charge, they're always going to radiate outwards. Conversely, if I have a negative charge in space, my field lines will always radiate towards the point charge. Right, and the reason for this is very intuitive, because the direction in which we assign our electric field, we said is the direction in which a positive test charge would move if it were placed in that field. And we all, I hope, know the rule that essentially that like charges will always repel one another. In other words, they'll always push away from another or from one another. And unlike charges, attract one another. Okay, so that's our general rule that we're going to be using. And if we use that rule in this example, what I then have is, you can imagine if I took a positive charge and I placed it somewhere within this field here, what's going to happen is that this positive charge will repel that one. And so wise here, we put a positive charge here, it's going to be attracted to the negative charge, and so it moves towards that charge. So that's the first point. The second point is that these field lines never ever cross each other. So that's the third point. So you can't have a field line doing this and a field line doing something like that. That's a situation that's illegal. They're not allowed to cross one another. The third point, which your teacher should have gone with you, is that the field lines are going to give us an indication of how strong the field is, because they are closer where the electric field is stronger. And finally, what we have is that they are always directed from positive to negative. Now, of course, that sort of goes with the first point, because the first point says they point away from the positive charge and always point towards the negative charge. So if I go back to my question, what I have in my question is I've got these two spheres, R and S, and we are asked to draw the electric field pattern due to these two spheres. Right? So how do I go about doing this? Okay. So the way I go about doing this is I've got my sphere R, right? And say here's my sphere S. Now remember that the charges on these spheres, it's no longer +8 and -4, because in the previous statement, we brought them together and we moved them apart. And so what I have here is that the charge on this sphere is going to be +2 microcoulombs, and the charge on this sphere is going to be +2 microcoulombs. Right? So what I then have is that the electric field lines, according to our first rule, always point away from a positive charge. So you can draw the field lines, say for the sphere on the right-hand side, and what I'll find is that those field lines will always point outwards. Likewise, for the left-hand side sphere, the field lines will always point outwards. Okay, but something interesting happens in this region here between the two spheres, because what can also happen is I cannot have a field line that points outwards and points outwards, right? Because the field lines are not allowed to cross, they're not allowed to touch each other. So what ends up happening is that these field lines that come out from this side start to bend away from one another. And you'll end up with this region where there is no electric field, right? It's this vacant area in the middle, and that's a consequence of the fact that the field lines cannot cross each other. And in this case, I've got two positive charges. Okay, so that would be question 1.3. Okay, now is everybody happy with that? Let me see if I can just see. Okay, I've got thumbs up. Okay, everybody happy? Going once, going twice. And let's move on to the next question. So the next question is a little bit more interesting. It mentions a free body diagram, which sort of brings to mind that we're now going to be working with forces. So it asks us to draw a free body diagram showing the electrostatic forces experienced. No, I've missed a whole chunk. What have I missed? Sorry. After R and S have been in contact and separated, a third sphere T of charge 1 microcoulomb is now placed between them, as shown in the diagram below. Okay, that's fine. So got T that's placed below 10 centimeters from R and 20 centimeters from S. And we are asked to draw a free body diagram showing the electrostatic forces experienced by this sphere T due to spheres R and S. Okay, so remember that in electrostatics, for our force, we have the Coulomb's law, right? So this is question 1.4, go back to my black pen, right? So remember that Coulomb's law tells us that the magnitude of the force is directly proportional to the product of the charges, right? Divided and inversely proportional to the square of the distance between them. To convert this from a proportionality to an equation, we introduce the constant of proportionality, which is K. I think, yeah, you guys call it K. So we end up with this equation that F is equal to K Q1, Q2 over R squared. Okay, now remember that this equation, we only use it to give us the magnitude of the force, right? So when you're using this equation with your Q1 and Q2, for this particular question, it doesn't matter because all the charges are positive, right? But even if a charge is negative, when you use this equation here, you should ignore the sign. You should ignore the sign. And in so doing, what you essentially do is you only find the size of the force or the magnitude of the force. And then in order to determine the direction, we use the fact that like charges repel one another and unlike charges attract one another, right? So in this here, we use this equation, Coulomb's law, and what this gives us is the magnitude of the force, and then this is the convention that we use, and this convention we use to determine the direction of the force, because of course, as we all know, or towards all have an inkling, force is a vector, and so a vector must have both a magnitude and a direction. I suppose it's a good point to mention, okay, If I do things a little bit differently to the way that you're used to seeing them, please just let me know. Our notations may be slightly different, but I don't want to cause any confusion. While I go through this, I've tried to stick to the notation that you should be using for your grade 12. But again, if there's any issues with regards to the notation, please let me know. So question 1.4 asks us to draw a free body diagram that shows the electrostatic forces that are being experienced by sphere T due to the two spheres R and S. Okay, so I'm quickly going to sketch this out now. So what this looks like is, okay, let me say that this is sphere T. I've got a sphere S here. And we've got the sphere R on the side. Okay, I know the distances. This is 0.1 meters. There's that distance. And this distance here is 0.2 meters. Okay, the charges, I've been given all the charges. I know that sphere R has got a charge of 2 microcoulombs. Sphere T has got a charge of 1 microcoulomb, and sphere S has a charge of 2 microcoulombs. Right? So we want a force diagram for T. So here is this T, right? And sphere T is going to fill R as well as due to sphere S. Now the magnitude of that force, we was in the next part of the question, but the direction is easy enough to guess, right? Because if I look at sphere R acting on sphere T, what happens is that both those two spheres are positive. And since both spheres are, they're going to repel. And if they're going to repel, what I then have is in this direction here, I'm going to have, this is going to be the force by R on T. So I want to push sphere T to the right. Conversely, at the same time, sphere T and sphere S are going to want to repel one another. And we'll have a force to the left. And this will be the force of sphere S on sphere T. Okay, is everyone happy with this before I continue? Okay, got a thumbs up, thank you. Can I just ask, is everyone happy with the speed I'm going at, or do you want me to speed it up a bit or slow it down a little bit? Okay, if anyone wants me to change the speed or adjust the speed slightly, please just pop it into the chat and we will go accordingly. Okay, so that is the force diagram for question 1.4, that is the free body diagram. Question 1.5 asks us to calculate the net electrostatic force experienced by T due to R and S. All right, so let me try and get a new page here. Okay, so now I need to calculate the net electrostatic force. So just to remind everybody that, just so that it's on this page here, and I don't have to keep going backwards and forwards, we had sphere T, S, and R. This distance was 0.1 meters. This distance here was 0.2 meters. This was 2 microcoulombs, 1 microcoulomb, and this was 2 microcoulombs. And what we've just shown on the previous one is that I've got this force by R on T, and there's also a force to the left, and this is a force by S on T. And 1.5 asks us to calculate the net electrostatic force. So to do this, we need the magnitude of the force, right? So the magnitude of the force, as we said in the previous thing when we talk about it, is going to be given by this expression here, Q1, Q2 over R squared. The direction is going to come from our law. So the direction comes from that like charges attract and, sorry, like charges repel and unlike charges attract. That gives us our directions. And just like you would have done for normal vectors and Newton's second law type problems, what you then need to do is, well, we need to pick a direction to be positive, right? And I'm going to pick, so I'm going to assume that things moving to the right are positive. So in other words, this direction here is going to be my positive direction. Okay, so the first thing I can calculate is I can calculate the force by S on T. So the shorthand for that is the force by S on T. So that's the shorthand here. When you see ST, it's by S on T is going to be equal to K, well, I know what Coulomb's constant is. It's on your data sheet. It's just 9 times 10 to the 9 multiplied by Q1 in this case is just R, or QR. So it's going to be 2 times 10 to the minus 6. Q2 is just going to be the charge on sphere T, which is 1 times 10 to the minus 6. And we divide this by the square of the distance between them. Sorry, I'm doing ST. ST, so in this case, it doesn't matter because they're the same. But so this is Coulomb's constant, right? So what I have here, this is K, this will be QS, and this will be QT, right? And we divide them, we divide it by the square of the distance between them, which is going to be 0.2 squared. Always important to remember to convert to SI units. SI units all the time. And if you put this on your calculator, what you should get is that the magnitude of this force is going to be 0.45 newtons, which means that the force by S on T, right? So I don't know if you guys use the overhead arrows or you underline your forces, but let's use overhead arrows for today. So the force is equal to 0.45 newtons and is acting to the left. All right, the second step is now to calculate the force by R on T. And in this case, it's going to be equal to K, which is 9 times 10 to the 9, multiplied by QR, where QR is 2 times 10 to the minus 6, multiplied by QT, which is 1 times 10 to the minus 6, over the distance between them squared. So the distance in this case is going to be 0.1 squared, and this will be equal to 1.8 newtons, which is the magnitude of the force. And so that means that the force by R on T is going to be equal to 1.8 newtons to the right. So as I said, we're going to let things to the right be positive. So therefore for us, the net force right? The net force, mixed notation, is going to be the force by S on T plus the force by R on T. And so this is going to be minus 0.45 plus 1.8. And this is equal to 1.35 newtons. And the direction is to the right. That's not how you spell right. Or you can say that it's something like 1.35 newtons towards here. Yes. Okay. Is everybody happy with that? So that was 1.5. Okay. 1.6 asks us to define the electric field at a point. Okay. So 1.6 asks us to define the electric field at a point. So you know the equation, it's on your data sheet, right? So from your data sheet, you have that the electric field is F over Q. So you don't have to really memorize the words because you can always work it out from the equations. And so when you're asked to define the electric field at a point, typically what they want you to do in that case is to define it in words rather than the equation, because the equation is already on your data sheet. And so the electric field at a point, right? The electric field at a point is the force experienced it's the force experienced per unit positive charge that is placed at that point. Okay. Now the key words here, it's the force experienced per unit positive charge, which you can see from the equation because per really means divide. So let's say divide. So it's the force experienced, which is F per divided by the unit of positive charge, which is going to be your Q. So if you ever forget it, you should always be able to work these things out from your equations. Okay, so 1.7 asks us to calculate the magnitude of the net electric field at the location of T due to R and S. And we are told to treat the spheres as if they were point charges. Okay, so calculate the magnitude of the net electric field at the location of T due to R and S. Okay, so I know from my answer to 1.6 that the electric field at the point is the force experienced per unit positive charge, right? So this tells me at point C, the electric field, right? The electric field is just going to be the force experienced per unit positive test charge. Now I know what the force is at T, right? Because when I was over here at 1.5, we worked out the net force at point T on the sphere T. We worked out what the net force is. The net force is 1.35 newtons. Right? So it's going to be, the force is 1.35. And I divide this by my positive test charge. Because remember, when we're looking for the electric field, we take our positive test charge and we place it at that point, and we see what's going to happen, right? And I know in this case, right, what is my charge? Oh, sorry, my thing doesn't want to go along. I've got a charge of 1 microcoulomb. Right? So at this point, what I have is I've got this charge of 1 microcoulomb at T, and I want to calculate the electric field that is due to this T and this whole setup. Well, I know what the net force is. I know what the charge is. The charge is 1 microcoulomb, which is 1 times 10 to the minus 6. And this one we don't need a calculator for. It's going to be 1.35 times 10 to the positive 6 newtons per coulomb. And you are done with the question. Okay, is another, I think that's the whole question. Yes, that is 1.7. So now I need some feedback from you guys. I need to know if everyone is happy and I can move on to question 2, or if there's a couple of things that need some clarification. You can pop it in the chat if you're happy, or you can unmute your microphone and say, I'm good. Just let me know that I'm not speaking just to myself. Okay, got some thumbs up. Okay, cool. Got like 4, 5, 6 thumbs up. Okay. So yeah, that should be fine, hopefully. So let us move on to the second question on electrostatics. And in this case, we've got 2 identical negatively charged spheres, A and B, having charges of the same magnitude, and they are placed 0.5 meters apart in vacuum. The magnitude of the electrostatic force that one sphere exerts on the other is 1.44 times 10 to the minus 1 newtons. Okay, and they want us to start off by stating Coulomb's law in words. Okay, but before I do that, let's just go through the question again and look at some keywords that you should be aware of. The first one is this identical, because it means it tells me that my spheres are exactly the same, right? They have the same magnitude. They are 0.5 meter apart. They're in vacuum, okay, which is important because it affects our Coulomb constant. But for you guys, I think you'll always be in vacuum. And I'm also told that the magnitude of the electrostatic force is 1.44 times 10 to the minus 1 newtons. Okay, those are sort of the keywords in there. And there's a diagram that accompanies this. So the first part of the question asks us to state Coulomb's law in words. So the way you can think of Coulomb's law is think of the equation again. So the equation, we sort of did this in the previous question, but the equation is F is equal to K Q1 Q2 over R squared. Okay. All right. So what you have here is that the magnitude of the force is proportional to the product of the charges, but the magnitude of the force is going to be inversely proportional to the square of the distance between them. And when you bring these two together, you essentially have that the magnitude of the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. And that is Coulomb's law. Okay, now when we do the equation, of course, the equation is equal sign. And so for the equation, I have that F is equal to K Q1 Q2 over R squared. And in this case, I can bring in the equal sign. And the reason I can bring in the equal sign is because I've introduced this K here, which is the constant of proportionality. Okay, so we should be able to use this, right? This is Coulomb's law in equation form inside this black box. And we should be able to use that and convert that to words. So let's give this a try now and see if we can get it right. So Coulomb's law states the following. It's the magnitude of the electrostatic force exerted by one point charge on another point charge right? So that's the left-hand side of the equation. The magnitude of the electrostatic force exerted by one point charge on another point charge is what is going to be directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Okay, so that's Coulomb's law, but as I said, you should be able to work it out from that expression in the black box. So if you're ever asked to write down Coulomb's law in words, it's this 2.1, which is an expression I'm sure your teachers have gone over with you. If you ever asked to state Coulomb's law in mathematical form, it's the black box. It's that the magnitude of the force is proportional to the product of the charges divided by the square of the distance between them. Okay, so that's 2.1. Now 2.2 asks us to calculate the magnitude of the charges or the magnitude of the charge on each sphere. Okay, so I need the magnitude of the charge on each sphere. And so I'm going to start off by using Coulomb's law, right? So Coulomb's law says that the magnitude of the force is going to be K Q1 Q2 over R squared, right? But what I know in this case is that my spheres are identical and are carrying charges of the same magnitude. In other words, Q1 is equal to Q2, right? And so what that means is I can write this as K Q squared over R squared. Okay, this first line here is just Coulomb's law. This second line here is since the spheres carry charges of equal magnitude. Or say carry identical charges. Right. So what I have now is that coulombs will becomes F is equal to K Q squared over R squared. And what we are looking for is we are looking for the magnitude of the charge on each sphere. In other words, what we are looking for is we are looking for Q. So I can rearrange this equation. And if I rearrange this equation, I'll get that Q is equal to the square root of F R squared over K, which is equal to the square root. The force I've been given is 1.44 times 10 to the minus 1. Right, that's the force. The distance, they're half a meter apart according to the question. So it's 0.5 squared. And we divide this by K, which is 9 times 10 to the 9. And if my calculator work is correct, this should come out as 2 times 10 to the minus 6 coulombs, which is just 2 microcoulombs. Right? So that's the magnitude of the charge on each sphere. Now, 2.2.2 asks us to calculate the excess number of electrons on sphere B. Okay, so 2.2.2 asks us to calculate the excess number of electrons on sphere B. So you'll remember that the total charge, Q, can also be written as the number of charges multiplied by the charge on each carrier, in this case, the charge on the electron. So the total charge, so that's what this equation is saying, is Q is the total charge that's equal to N, where N is going to be the number of charges, and E is just the charge of one electron. Okay, now in this case, I'm looking for a number, so we use the magnitude of the charge. You may ask yourself, okay, why am I using electrons? How do I know when to use electrons and when to use protons? Well, in this case, the spheres are negatively charged, right? And because they're negatively charged, what it means is that they have an excess of electrons. So at some point during your studies, you would have come across the idea that we have these two charges, positive and negative, and the carriers we associate them with are electrons, which normally have the minus, which normally have E minus as the symbol, but they're also protons, which you guys I think note as a P plus. And the electron and the proton have the same magnitude of charge, just different signs. So the charge on the electron is minus 1.6 times 10 to the minus 19, while the charge on the proton is 1.6 times 10 to the minus 19 coulomb. Okay, and it turns out that the electron, and so I suppose in consequence, the proton, that's the smallest unit of charge you can have. And so it's indivisible. It always must be a whole number. And essentially that's this equation that I've written for 2.2.2. So to work out the number of electrons, number of excess electrons in this case, right, the number of excess electrons in is just then going to be the charge divided by the magnitude of the charge on a single electron, the total charge divided by the charge of one electron. And in this case, The total charge is 2 microcoulombs, which is 2 times 10 to the minus 6. And I divide this by the charge on the single electron, which is 1.6 times 10 to the minus 19. And what I then have is that the number of excess electrons must be 1.25. And if I've done this correctly, I can get 13 times 10 to the 13 electrons. Okay, and I hope that that is clear. I hope that that is clear. So that's how you find the number of excess electrons on something, or the number of excess charge carriers. Yes, I see a hand up. Please, you can put it in the chat, or you feel free to unmute. Yes, with the hand up, Oppo CPH2271. Okay, I see a hand up, but I can't see. Okay, so why don't I use the positive value to divide it? Okay, it's a good question. So the reason I use the positive value to divide is because we're looking for the number of charges, right? Now, for the number of charges, I know that, if I tell you that if I give you 10 sweets, you have 10 sweets, it's going to be positive. So even though the charge on the electron is negative, when it comes to this equation here, what we're dealing with here is we are dealing with magnitudes. It's a very good question. Thank you. I should have been more specific. Right? So this is the magnitude of the total charge is equal to the number of charges multiplied by the magnitude of the value of the single charge. Because the number at the end must be positive, right? Because it doesn't make sense. So it gets a little confusing if you start saying that I've got -1 times 10 to the 25 electrons, for example. So if you just stick to magnitudes, it'll give you the number of electrons, right? The one time you can't stick to magnitudes is if I want the actual charge, not the magnitude of the charge, because in 2.2.1, what we calculated was the magnitude of the charge. So I hope that guy perfect. I got a thumbs up. So guess okay, that's cleared up. So we've calculated the number of excess electrons on the sphere. 2.3 says that P is a point at a distance 1 meter from sphere P. And they want us to calculate the direction of the net electric field at point P. Okay, so in this case, I've got A and B. So this is 2.3.1. Go back to my black pen, right? Right, and so in this case, what do I have? Well, I've got A. I've got B. And I've got this point P. Right? And on the left here, the charge on A is -2 microcoulombs. The charge on B is -2 microcoulombs. Okay. Now remember, here in 2.2.1, so there should be 2.2.1. In 2.2.1, we just calculated the magnitude. So I just have the magnitude, but I know it's negative because the question tells me that they are negative. What's happened there? Switched across the pages. Right? And so now I've got this point at P. And what I want to do is I want to calculate the direction of the net electric field. Right? So it's very similar to what we did in the first question, slightly different, but also similar, as you're going to see. So you know that the electric field, just remember that the electric field, we said is going to be the force per unit charge. So if you imagine you put some charge here, doesn't matter what it is, call it QP, right? And I want to calculate the field at P because of A. The field at P because of A, which I'll call EA, is just going to be the force, which is the Coulomb force, which is K, the charge at A times the charge at P over R squared times the charge at P. So what happens is that the charge at P cancels out, and I find that the electric field at point P, due to the field at A, is just going to be given by K QA over R squared, where R in this case is the distance between A and P. Excuse me. So I can actually call this RAP to make it absolutely clear. Right? So that's from the definition of the electric field. And basically that's the formalism we're going to use. Right? So I'm going to have that the net electric field for the total electric field is going to be the electric field due to the charge at A plus the electric field due to the charge at B. Okay, so we can go through this now. So the electric field due to the charge at A is going to be K times the charge at A right? What am I jumping ahead here? Calculating the number of electrons. Sorry, I do apologize. Question 2.3.1 is a lot simpler. They just asked us to calculate the direction of the electric field. So if we just want the direction of the field, what you can then do is pick a direction to be positive. Right? So, okay, forget this business here. Get this business here for now. We just want the direction. Right? So you can see from this expression here, or rather it actually comes out from the equation here, that the direction of the electric field is the same as the direction of the Coulomb force. So if the Coulomb force is to the left, then the electric field vector will point to the left. Likewise, if the Coulomb force is to the right, then the electric field vector will point to the right. Right? So what you do in this case is imagine that we take a positive test charge. Right? So I take a positive test charge and I stick it at P. Right? And my positive test charge is this QP business. Right? So what's going to happen is that both A and B are negative. So in this case, there's going to be an electric field to the left, right, due to this attractive force that exists between A and P. And there's going to be a field to the left due to this attractive force that's going to exist between B and P. So overall, they both point to the left. And so my overall electric field should be to the left. Right? So to answer 2.3.1, it's a lot more straightforward than what I was doing. Right? To answer 2.3.1, it's just to the left. How many marks is that for? 1 mark. Okay, that makes a lot more sense. It's to the left. It's to the left, and the reason that it's to the left is you imagine a positive test charge at P, And I know that, unlike charges, attract. So if I put my positive test charge at P, it's going to move to the left. And remember that the positive test charge moves in the same direction as the field. So if the charge moves to the left, it means that the field must be pointing to the left in this case. Okay, so I see we're nearly out of time. Well, we're basically out of time, but I'd like to finish this question. So I apologize for being over time. But if you could stick with me just through to the end of 2.3.2. Right, because 2.3.2 asks us to calculate the number of electrons that should be removed from sphere B so that the net electric field at the point P is 3.10 times 4 newtons per coulomb. Okay, so what I need is, I need space. Okay, let me just transfer this problem here. So now we're doing 2.3.2. Okay, so what we can do in this case, we need to assign directions. So the first thing I'm going to do is I'm going to take to the right as positive. Right? And why do I take to the right as positive? It's because I know that the question has asked me that we need to set this up so that the net electric field at point P is to the right. Must be positive to the right. So when I'm assigning my directions, I must take to the right as positive. Then we can calculate the net electric field. And for that, we have that the net electric field is equal to the electric field due to charge A plus the electric field due to charge B, right? And as we've spoken about, this becomes K QA over R AP squared plus K QB over R BP squared. Okay, now I think you went to the distances. This was 0.5 meter. And point P was 1 meter to the right. Okay, so remember, hopefully it's the last time I need to flick across. What we're going to do now is we're going to calculate the number of electrons that we're going to remove from sphere B so that the net electric field points to the right. So imagine we've got some process where you can go to sphere B and we start picking off electrons. We're going to start picking off electrons until sphere B goes from being negatively charged to being positively charged. And then we're going to keep picking electrons off until we have a positive charge on sphere B that points to the right. And that's big enough to overcome this point A, such that the net electric field is just 3 times 10 to the 4 business. So what that means then is that I've got the net electric field, which is going to be 3 times 10 to the 4. Right? This is what I want my net electric field to be. 3 times 10 to the 4 newtons per coulomb. This is going to be equal to K, which is 9 times 10 to the 9, multiplied by QA, which is 2 times 10 to the minus 6, over the distance between A and P, which is 1.5 squared, plus K, which is 9 times 10 to the 9, multiplied by whatever the final charge is going to be on B, which I'll call QBF. In this case, the F just stands for final. And this I divide by the distance between B and the point P, which is just going to be 1 meter squared. Okay, so you need to put this on your calculator and you can solve for QB, the final charge QBF, and in this case, the final charge must be 4.22 times 10 to the minus 6 coulombs. Now, if the final charge is equal to this number, right, then the net electric field is going to be the 3 times 10 to the 4. But what this is, right, this is the final charge on sphere B, and we need to use it to find the number of electrons. And how do we find the number of electrons? Well, this is fairly straightforward, right? So the number of electrons on sphere B now is just going to use our equation. Q is equal to ME. I know what Q is, so it's going to be 4.22 times 10 to the minus 6 is equal to N times 1.6 times 10 to the minus 19, and therefore NF is equal to 2.64 times 10 to the 13. But I know from the previous question, right, but from 2.2.1, I know that the initial number of electrons was equal to 1.25 times 10 to the 13, right? And therefore, if I know how many electrons I started off with and what the deficit in electrons I have at the end is, I can calculate the number of electrons that have been removed, right? So the electrons that have been removed is going to be equal to NF plus NI, right? So this is going to look a little strange because the first thing that should be going through your mind is why am I adding them? Usually when you do the difference, it's final minus initial, but in this case, I'm saying it's NF plus NI, right? The reason for this is because remember, sphere B starts off negative. What we then do is we remove charges. So this Ni here is the number of electrons that we remove. To make sphere B neutral. In other words, if we remove this Ni number of electrons, sphere B goes from being negatively charged to having an overall charge of 0. It goes from being negatively charged to neutral. What I then do is I remove more electrons, right? How many more? Well, enough to get me all the way to this NF, right? And so these are the electrons that must be removed to make the charge on sphere B positive. In other words, to make sphere B positive, and that's why we add them. Okay, and so this is then going to be equal to, what is this? This will be 2.64 times 10 to the 13 plus 1.25 times 10 to the 13, which is 2.64 plus 1.25 is 3.89 times 10 to 13 electrons. And therefore, if I remove this large number of electrons from sphere B, goes from being negatively charged all the way through to being positively charged, and it ensures that the net electric field at point B is then given by this 3 times 10 to the 4. Okay, so that's going to be it, I think, for today's session. I'm a little bit over time. There was a register that was shared earlier. If you haven't done so, please can I ask that you complete the register? And there's normally a form link. Okay, my chat has just disappeared, but there is normally a form that you can also just ask to fill in just to rate the session. So we do that because it helps me know whether or not I was going at the correct pace. So I hope that you found that okay. Before I go, Londiwe, I see you've unmuted yourself. Do you have a question? I can share my screen again. Okay, Londiwe, I can't hear you. Okay, you don't have a question. Okay, if you don't have a question, then I hope everyone found it helpful. If I went too quickly, just please let me know. Just please let me know. You know, on the form that you used to sign up for this, there was an email address that you could send your queries to. Dogoza says he's going to resend the links shortly. If you haven't seen the links for the register or for the survey to say if you found this useful or not, I hope to see you all next week, Wednesday. I think it was the electrostatic section, if I remember the timetable correctly. We will be going over it again on Wednesday. We'll be carrying on from this and we'll go to more complicated problems, provided that no one has any questions from today's session. If you do have a question from today's session, please feel free to email. There's a helpline email where you can send your queries, and there's a tutor who's assigned to that. They will get back to you. Otherwise, please bring your questions to the session next week. You can also email that tutor if there is something specific that you'd like me to cover, and I'm happy to do that. Otherwise, I wish you all a good evening. See, I'm still screen sharing. Should probably stop that. Otherwise, I wish you all a good evening, and I hope to see you next week, Wednesday. Goodbye.